What if I told you that an object in deep space just pulled off a maneuver so precise that it's like throwing a needle from Los Angeles and hitting the edge of a coin standing upright in New York? You'd probably call it impossible. And in a universe ruled by chaos, gravity, and astronomical odds, you'd be right. And yet, it just happened. Astronomers named the object 3IATLAS. At first, it appeared as nothing more than a faint blip, a weak signal buried inside raw data streams from over 200 independent observatories around the world. Objects like this are detected all the time. Most are ignored. Most are predictable, but this one wasn't. As the data was refined, something unsettling emerged. The trajectory of 3IATLAS did not belong to the sun. It came from interstellar space, the vast silent void between star systems where gravity no longer answers to our solar neighborhood. Then came the number that froze the room. The margin of error in its projected path was just 1 in 26,000. To put that into perspective, imagine closing your eyes, standing on the west coast of the United States, throwing a needle and watching it land perfectly on the razor-thin edge of a coin thousands of miles away. As 3IATLAS raced toward Jupiter, it approached an invisible boundary known as the Hill Sphere, the region where a planet's gravity begins to dominate space itself. This zone is infamous. Orbits bend, paths distort, predictions usually break down, but this time they didn't. The data wasn't messy, it wasn't noisy, it wasn't random. It was clean, mathematical, almost deliberate. The silence of interstellar space had been interrupted, and within the first moments of observation, 3IATLAS forced scientists to confront a question they weren't prepared to ask. Was this simply the rarest cosmic coincidence imaginable, or the first hint that something out there is far more intentional than we ever expected? This was not humanity's first encounter with an interstellar visitor. Before 3IATLAS, we had already been startled by two famous outsiders, Oumuamua in 2017 and Borisov in 2019. Oumuamua arrived and left almost in silence. No visible comet tail, no obvious gas plume, no clear signs of activity. Its strange shape and unexplained acceleration ignited years of debate, debates that still haven't fully settled. Borisov, on the other hand, behaved exactly as expected. It looked like a classic comet, ice, dust, outgassing, a familiar story written in cosmic shorthand. Interesting but not disturbing. 3IATLAS is different. From the very first measurements, astronomers noticed something extreme, its velocity. It was moving faster than any interstellar object ever recorded, passing through our solar system. Its path was unmistakably hyperbolic, a one-way trajectory. It was not captured by the sun, it was never going to stay. But speed alone wasn't what set off alarms. Unlike Oumuamua, which appeared almost physically silent, 3IATLAS showed clear signs of activity. Subtle but consistent fluctuations in brightness suggested material was being released from its surface. In other words, it was doing something. That behavior is common in comets, but what wasn't common was how controlled it seemed. When scientists examined the early spectral data, faint but persistent signatures began to emerge, traces of carbon-rich organic compounds, not evidence of life, but undeniably the chemical building blocks associated with complex molecular structures. Here's the problem. In interstellar space, objects are exposed to relentless cosmic radiation for millions, sometimes billions of years. Organic compounds should degrade, they should vanish, unless they are shielded, replenished, or formed in conditions we don't yet fully understand. Placed side by side, the contrast became unsettling. Oumuamua was a silent anomaly. Borisov was a familiar traveler, but 3IATLAS behaved like a dynamic system, active, responsive, and chemically intriguing. It didn't just pass through the solar system, it engaged with it. At this point, the question stopped being what kind of object is this, and quietly transformed into something far more uncomfortable. Are we looking at an extraordinary, rare natural phenomenon, or the first sign that our current models of interstellar physics are missing something fundamental? If 3IATLAS were nothing more than an interstellar rock slowly evaporating under the sun's heat, the story could have ended there. But the problem is it didn't behave that way. As 3I-ATLAS passed through perihelion, the point where it came closest to the sun, astronomers expected a familiar process. Rising temperatures should trigger outgassing, jets of gas and dust escaping the surface, producing small thrusts in random directions. This normally causes objects to tumble, wobble, and drift unpredictably. That's how nature usually works. But the data told a different story. After perihelion, 3I-ATLAS began to accelerate, not suddenly, not chaotically, but in a way that was smooth, directional, and sustained over time. That alone raised eyebrows. In astrophysics, natural outgassing rarely produces a clean thrust vector. Comet surfaces are irregular, cracks open unpredictably, pressure fluctuates. The result is almost always instability, rotation, tumbling, noise in the data. But 3I-ATLAS was not tumbling. Measurements of its rotational state showed a surprisingly stable axis. The acceleration remained aligned along a consistent direction, as if the force behind it were being continuously maintained rather than randomly triggered. Then came something even more unsettling. As 3I-ATLAS moved farther away from the sun, the uncertainty in its projected trajectory didn't grow, it shrunk. Each new observation didn't introduce more chaos, it refined the path, smoothed it, locked it more tightly into mathematical predictability. That's not how passive natural systems usually behave. In science, nature tends to introduce noise. Machines tend to introduce patterns. This doesn't mean 3I-ATLAS is a spacecraft. That conclusion would be irresponsible, but it does force researchers to acknowledge an uncomfortable reality. Standard physical models are struggling to fully account for what's being observed. Some attempted to explain the acceleration through exotic forms of outgassing, hydrogen ice, nitrogen sublimation, or deeply buried volatile layers releasing energy with uncanny precision. Each explanation required increasingly fine-tuned assumptions. At a certain point, coincidence begins to look less like chance and more like constraint. By now, the question was no longer whether a non-gravitational acceleration existed. That was clear in the data. The real question had shifted. What kind of force produces sustained directional acceleration without rotational chaos in an object that has traveled through interstellar space for millions of years? And more unsettling still, why does its path look cleaner the farther it goes? To understand why the acceleration of 3I-ATLAS truly unsettled the scientific community, we need to pause and examine a principle of physics that most people outside aerospace engineering have never heard of, the Oberth effect. Imagine standing on a spinning playground carousel. When it's turning slowly, you jump off and travel only a short distance. But if you wait until the carousel is spinning at its fastest, then jump, the same effort sends you flying much farther. In orbital mechanics, the faster an object is moving, the more effective any applied thrust becomes. A small push at high speed generates a disproportionately large increase in orbital energy. And the moment of high speed is perihelion, the point where an object passes closest to the sun. This isn't speculation, it's a cornerstone of spaceflight. Human-made spacecraft have exploited the Oberth effect for decades. Engineers plan tiny burns at precisely chosen moments to radically reshape trajectories while conserving fuel. Timing, not force, is the key, and this is where 3I-ATLAS becomes deeply unsettling. The data shows that its non-gravitational acceleration did not occur randomly. It peaked exactly when its orbital velocity was highest, the precise moment when, according to the Oberth effect, thrust produces maximum energy gain. That coincidence alone forced scientists to stop and think, because if this acceleration were caused by natural outgassing, its timing should be dictated by surface temperature, internal fractures, and material composition, chaotic variables that have no reason to align with a mathematically optimal orbital window. In other words, nature does not know about the orbital effect. Engineers do. What makes this even more troubling is what happens when researchers run simulations. Millions of natural scenarios were tested: uneven ice distribution, surface cracking, exotic volatile compounds, delayed sublimation from subsurface layers. The probability that a purely random physical process would consistently activate at the exact energy optimal moment turned out to be vanishingly small. So small that it approaches the threshold of statistical absurdity in precision science. And remember, this wasn't a brief impulse. The acceleration of 3IATLAS was sustained, stable, and long enough to fully exploit the Oberfläche, maximizing its outbound energy with extraordinary efficiency. If this were a spacecraft, it would be operating in a manner that aerospace engineers would describe as textbook perfect fuel optimization. But even if we completely discard the artificial hypothesis, problem remains. How does a natural process choose the right moment so precisely? This is where the debate stops being philosophical and becomes methodological. Science does not reject uncomfortable data. Science demands that we confront it honestly. At this stage, 3IATLAS is no longer just challenging our understanding of interstellar objects. It is challenging our assumptions about randomness itself, because when timing aligns this perfectly with theory, not once but continuously, coincidence begins to lose its explanatory power. And that is why in quiet conference rooms and late-night data reviews, scientists stopped asking whether the acceleration was real. They began asking something far more unsettling. What kind of process, natural or otherwise, behaves as if it understands orbital mechanics? When data refuses to be ignored, science does what it has always done best. It puts every explanation on the table and eliminates them one by one. The first hypothesis was the simplest: observational error. Perhaps the telescopes were wrong, perhaps the measurements were noisy, perhaps this was nothing more than a statistical illusion. But this idea collapsed almost immediately. More than 200 independent observatories using different instruments and methodologies converged on the same trajectory. When uncertainty shrinks instead of grows, science no longer calls it error. The second hypothesis sounded far more reasonable: natural outgassing. This is the standard explanation for non-gravitational acceleration, but in the case of 3IATLAS, it became increasingly strained. Natural outgassing produces irregular thrust, fluctuates over time, and almost always induces tumbling. Yet 3IATLAS displayed a stable directional force vector, sustained over time with minimal rotational disturbance. To keep this explanation viable, researchers had to introduce increasingly artificial assumptions: deeply buried volatile layers, perfectly asymmetric release patterns, and timing that just happened to align with the Oberth optimal window. Each added condition made the model less natural, not more. The third hypothesis was skepticism's final refuge: pure coincidence. The idea that the universe occasionally produces extraordinarily rare alignments, and that this was simply one of them. But science does not evaluate coincidence emotionally, it evaluates it statistically. When the probabilities are compounded, hyperbolic trajectory, directional acceleration, optimal timing, shrinking error margins, the combined likelihood becomes vanishingly small. At some point, coincidence stops being an explanation and starts becoming a placeholder for ignorance. That left only the fourth hypothesis: controlled motion or an unknown structure. This does not mean declaring 3IATLAS a spacecraft. That conclusion would be premature. But it forces open two uncomfortable possibilities. Either we are observing a fundamentally new form of interstellar matter with dynamic properties not yet described by current physics, or we are witnessing a system whose motion exhibits a degree of control beyond familiar natural processes. Science does not like this hypothesis, but science does not get to discard it simply because it is unsettling. At this stage, the balance had shifted. The question was no longer which hypothesis feels acceptable. It became something far more precise and far more dangerous. Which explanation contradicts the data the least? And disturbingly, the answer was no longer obvious. In 2026, 3IATLAS approached a crossroads that no astronomer could ignore: Jupiter's Hill sphere. This is not a physical boundary, but a gravitational one, the region where the largest planet in the solar system begins to dominate the surrounding space. For most small bodies, this zone is where trajectories bend, predictions falter, and chaos often emerges. Scientists prepared for three possible outcomes. The first scenario was fragmentation. If 3IATLAS were structurally fragile, Jupiter's tidal forces could tear it apart, releasing debris, a familiar fate for many cometary bodies. The second scenario involved intense material release. Entering a new gravitational regime could trigger internal reactions, producing strong outgassing events and sudden changes in motion. The third scenario was a trajectory deflection, an unexpected gravitational interaction that could send the object onto a radically altered path. To witness this moment, Earth-based telescopes were not alone. Spacecraft already operating in the Jovian system, including Juno and JUICE, were oriented to monitor any anomalies and plasma fluctuations, magnetic disturbances, subtle variations in light and particle emissions that ground observatories could never detect. Then the data arrived. 3IATLAS did not break apart. It did not erupt, and it did not lose control. Instead, it passed through Jupiter's Hill sphere with remarkable stability. There were minor perturbations, exactly what physics predicts, but no signs of structural failure or chaotic motion. More surprising still, instruments detected subtle changes in its behavior, small but organized energy redistribution, low-level material release with directional consistency, and a slight refinement of its trajectory, as if the system were adapting to a new gravitational environment. These accidental observers, spacecraft positioned where Earth could never be, provided a perspective no one had anticipated, and slowly a clearer picture emerged. 3IATLAS was not a passive cosmic relic. It was a dynamic system, one capable of responding, adjusting, and maintaining coherence under extreme gravitational stress as it exited Jupiter's sphere of influence and continued its journey out of the solar system. 3IATLAS left behind more than data. It left behind implications, because after Jupiter, it was no longer reasonable to describe 3IATLAS as merely unexplained. It had demonstrated behavior, and behavior demands explanation. When 3IATLAS left the solar system, it did not take answers with it. It left behind questions. For centuries, we have treated interstellar space as emptiness, silent, inert, and largely uneventful between the stars. 3IATLAS challenged that assumption. It arrived from the void between star systems. It moved with unsettling precision. It responded, adapted, and maintained coherence where natural processes usually produce chaos. Perhaps 3IATLAS is an extraordinarily rare natural phenomenon, so rare that we simply haven't encountered it before. If that is the case, it forces us to rewrite textbooks on interstellar matter, orbital mechanics, and the range of behaviors the universe can produce over immense timescales. Or it may be something else entirely, not proof of extraterrestrial intelligence, not a declaration of alien technology, but a quiet reminder that our understanding is incomplete and the universe is under no obligation to behave according to the models we find comfortable. Science does not advance by avoiding uncomfortable data. It advances by confronting it, measuring it, and asking better questions. 3IATLAS did not answer whether we are alone, but it reframed a more fundamental question: